怎么平时没有 assignment 的咩？平时没有讲 CA 啊？有不？OK，然后 assignment 是什么情况呢？几个 assignment？4个，不是平均分配咩？4个。
前面他第3个同学，后来可能就是
急的跳跃啊？
最老师喜欢这样，可是密测的时候
很简单，
很难。之前我们第一个项目是6万千万，他密测的到时是想不到。
OK，然后变简单，然后这次是很简单，然后就变难。
突然，一切都突然。
OK。
礼拜几？
拜3。
我就要拜3次。
哎，来了，也是又来了。Nice。才不是换发型啊，金发。哎，有没有换发型？
看来在看睡前。
不是啦，看着看，你的看。Okay, today I bring some snack here, maybe not enough to share, so please share around among yourself to keep you awake. Okay, so as I warned you last time, right, our proof is getting more constructive and more involved now. But the good news is our test is passed until the part Tick's extension theorem. So whatever we do for this week and next week won't be tested. But it's for the completeness of these course. Okay, so you know these knowledge because these knowledge will be used in different area of research. Okay, no? So for now, I want you to change your way to listen to lecture. Okay, I want you to change your way to listen to lecture. I want you to treat it as a seminar. Okay, so what do I mean by seminar here? So maybe I won't say everything in detail. Maybe I will sketch most of the thing, but you're still allowed to ask questions. Okay, so you can ask. Maybe I won't go detailed explanation anymore because now we need to put everything together. The detailed things already do in previous week already. Okay, just that you need to recall everything back. Does it make sense? Okay, so no need to copy or what. I want you to train your listening. Okay, train your listening. Okay, listen to a seminar like that. So how the idea flow, why this idea will connect to the next idea. You can ask. I can choose to answer or not, or I can leave it otherwise. But you should ask whenever you have problem or you don't understand. Does it make sense? Okay, no? Okay. Because yeah. So treat it like a seminar. Some of the things I'll go fairly quick. Okay, so first theorem we're gonna prove today is Tychonoff theorem. So what is about Tychonoff theorem here? So the theorem here is about arbitrary product of compact space is compact. So last time what we proved is for finite case. Okay, we use the tube lemma thingy. So we cover one line first and then we consider all the horizontal component. So now we're going to prove arbitrary product. Okay, so in case of a arbitrary product, we can't use the same tube lemma before, so we need to use other machinery. Okay, so actually the main tool we're going to use is Zorn's lemma. So we will prove two results. I mean, one result before we go on to a Tychonoff theorem. So to prove the theorem we're going to use, we need Zorn's lemma. So we need to assume Zorn's lemma is true first. So what is Zorn's lemma? Let's remind ourselves. So suppose X is a non-empty partial order set. So recall what's a partial order set means. Meaning what? Yeah. Or another way is you can have a comparison between two elements. Okay. Compare between two elements, but not everything can be comparable. Okay. Partially ordered. And every totally ordered subset of X has an upper bound in X. So what does this mean? So you take a subset from your partial order set, but inside this set, everything can be comparable. So it forms a line, a chain. Okay, it's totally ordered. Okay, in this subset. So you need to consider every subset. Okay, every subset. Then this X has a maximal element. Okay, maximal element. There's an element that is greater than everything. Okay, everything can compare to this X. Okay, if this is true. It turns out that this result is quite hard to prove. It is equivalent to axiom of choice. Okay, that's axiom of choice. We didn't prove this in class as well. We just stated. Okay, so this is actually equivalent to axiom of choice. Does it everyone follow this? So if you have two property, so you need to look at this long sentence, you need to split into two parts, right? Two conditions here. Okay. So one condition is X is partially ordered, and then every totally ordered subset of X has a upper bound. Then this set has a maximal element. So this element can compare to everyone. And then everyone is less than it. Does it make sense? What's the significance here? You only know there's upper bound for every totally ordered set before. You don't know whether it exists for all, but turns out that it is true. And this is a quite strong result, although we just call it a lemma. Okay. Does it make sense? Okay, now can you imagine or not? You need to imagine, you cannot just look at the word. You need to imagine what is going on. Okay, this is how you listen to seminar. You need to imagine what people are saying. Otherwise, you will get sleep easily. Okay. Okay. So using this Zorn's lemma here, we're going to prove a theorem called the Alexander subspace theorem. Subbase. Okay, so what does this Alexander subspace theorem do? So let's consider a topological space with subbases C. Let's use X so that we don't confuse. Then X is compact if and only if, you want to guess? What's the sensible thing to write here? Every cover of X by subbasis element from X has a finite subcover. Actually, last time we proved a similar result, right? What did we prove? S is compact if and only if every open cover by basis element has a finite subcover. So it turns out that when you go to subbases, that become harder. Okay, become harder. So that's why we attach a name there, Alexander. Okay, become harder. Basis, last time we discussed already, not too hard. But it turns out that this theorem here, you need Zone's lemma. Okay, so let me give you a head out. This theorem, this proof is quite, I'll say, quite abstract. So why do I say abstract? Because we will go down and go out a few levels. Okay, for example, we will consider a collection of open cover. Okay, and then we will look at each element inside cover, what happened. Okay, so be careful with the notation later. Okay. All right, so actually one direction is easy. Okay, let me test Leongyuan again. Which direction is easy? Direction is to prove, right? If only if. Right, same question. Similar question to last time. Which direction is easy? What's Q, what's P? Mm-hmm. Why? By what definition? Say. How? Compact definition is what? What has finite subcover? But subbases might not be a basis, right? The way you generate topology using subbases and bases is different. In subbases, you need to consider finite intersection. But bases, you just take union only. It's a different way to generate topology. So subbases is not basis. Just now I explained. Did you listen just now? So what is subbasis? Generated by subbasis, what does it mean? You need to take union of finite intersection. But basis, you just take union of basis element. It's a different construction. Okay. What is the definition of compactness? Let me ask you again. What's the definition? Go find it. Go find. Go find it. What's the definition of who can help him? Every open cover have a finite subcover. So what does open cover mean? A covering of open set. Any open set. Okay or not? Okay. So I'll ask you again, which direction is easier? Brian? Why? Why? How? So? Yeah. So in this case here, the open cover we take here is element of subbasis. So element of subbasis is still open. So it is one type of open cover. So by compactness, all these open cover has a finite subbasis. In particular, open cover by subbasis element also has a finite subcover. Okay or not? You understand? 这个很重要哦，你要知道哪一个比较 general，哪一个比较 specific。general 东西可以 apply to specific，但是 specific 的东西不可以 apply to general，明白吗 ？OK， 方向啊，很重要。Okay, so one direction is easy, so left to right is obvious. So the hard word is right to left. Okay, the hard word is right to left. So what we do is we will argue by contradiction. Okay, so if I want to argue by contradiction, what do I need to suppose? Suppose that X is not compact, but every cover of X by subbasis element from X has a finite subcover. Is everyone following? There's no proof yet. I just use some logical statement. Okay, so what's the construction here? Since I have the since I have what? I'm not compact, right? So what can I consider? I can consider the collection of all open cover such that it has no finite subcover. Does it make sense? So what's the element here inside here? Set of open cover. Open cover is what? Set of open set. Does it make sense? So this thing is a set of set. Okay, set of open cover such that this open cover doesn't have finite subcover, because I say that it is not compact. Correct or not? There should have some, it's not empty here. Okay, but you can put a order on this set. Okay, what order can you put on here? Yes, so you can put subset inclusion. So you can put it is partially ordered by set inclusion. Do you know what it means? So if A less than B, meaning A is a subset of B, that's all. Okay, if you cannot say A is subset of B or B subset of A, then you don't know whether what they are less than or greater to each other. Does it make sense? Okay, if you are a subset to the other, then you are smaller than the guy. Make sense? Okay, so it's partially ordered. Okay, and then so you see, we're gonna use Zong's lemma, right? How to use Zong's lemma then? I have a partial order set already. What's the second criteria for Zong's lemma? Every totally ordered set, I have to found an upper bound. Okay. So now, if I want to use Zong's lemma, I need to proceed to the totally ordered subset. Okay. So let's take any partial totally ordered subset. Okay. We want to prove that there is a upper bound inside here. Okay. So that we can use Zong's lemma. Okay. Suppose this is a totally ordered set. So meaning I can put them in a chain. Okay, I can put in a chain. I know who is greater than who for everyone. So I can compare them to put into the chain. Then who is the upper bound here? Can you put the X as an upper bound? You mean such basis? Space X. I mean your upper bound should be choosing from the element of this collection, right? Okay. You need to consider open set. Sorry. Yeah, the X not necessarily is in the element of open cover. True. Yeah. True. Yeah. So what's the obvious upper bound here? Who is greater than everything here? Yes, you can just take the union. So because we are just looking for the subset inclusion, right? So we can check that OOJ is in the union of the whole chain here. Okay, so this M is an upper bound of who? Of this set here. Okay. So if we can argue that this guy belong to all, then we can start using Zong's lemma. Okay. Is everyone following? Okay. If you think you are left out, please ask. Please ask. Please stop me. So your goal is to stop me. My goal is to finish my work. Okay. So we have this contradiction loop going on. This is how teaching and learning process will occur. Where I cannot just things like sign knowledge 今年好吧，不可能的，就是你要反馈，我们有 feedback。Okay, so everyone's all good. So now if we can view that this guy M is in the set of all, which is the open set that doesn't have a finite subcover, then we can use Zone's lemma. Okay, later I'll tell you how we use Zone's lemma. Okay, so to show that, yeah, go question. Yeah.
It's a pre-ordered subset of, I mean, it's not necessarily finite, so it's a finite subcover.
Say again.
I mean, OI could be a finite subcover. If it's just a subset of O, it's not necessarily finite.
What's the problem here? What's the goal?
Why OI thinks it's finite?
Why OI is? I didn't claim OI is finite, right? I didn't claim. I just want to check this property here. Each OI is an open cover, is a set of open set. Each OI is a set of open set. Okay, so I want to prove that this union here live inside O. What is O? You need to be a open cover that has no finite subcover. So you need to show two things. Okay, you need to show two things here. Open cover and no finite subcover. Is it an open cover of X or not? Yes, right, because every OI already cover X. So I just take more things to cover X. So first, obviously, M is an open cover of X. Okay, so how to prove there's only it doesn't have finite subcover? Use contradiction. Okay, use contradiction. Yeah, contradiction is very good. Very good. So contradiction, contrapositive, all very good. Because contradiction will give us extra condition to prove. Otherwise, you need to show, you need to find or what. Okay. So suppose, on the contrary, that M has a finite subcover. So meaning what? Meaning there are finitely many sets in M. Okay. That cover X. Okay, that cover X. But what? Okay, such that if you like, I write down for you. I equals to 1 to n, such that X is in here. Maybe it's equal to X because our X is the whole space. Okay. But what? But OI is also open cover. OI is also open cover. Okay, so there exists so for every k in 1 over n, there exists IK such that UK is in OIK. Okay. Okay, because O itself is an open cover. Okay, so since IK are finite, okay, we can find n of them, and OIKs are totally ordered. Okay, we pick from the totally ordered subset. Okay, what we can see is, what can we see here? What can we see here is U1 up to UN live actually inside one OM because our OM is totally ordered. Totally ordered means what? One contained in the other. Okay. So if you contain in some OK, right, you can find the largest OK that contain all of them. Okay, no? Does it make sense? You are inside one OK, but all the OK line up. Okay, so everyone will be under one of the OK. Does it make sense? Because OK is totally ordered. That means what? This is a finite set in this particular OM here that has a finite subcover. Okay, so contradict that. OM having no finite subcover. Okay or not? Okay, so contradiction. Okay, so this means what? Then mu is in O. Okay, so then Zone's lemma apply. So what does Zone's lemma give us? So Zone's lemma will tell us that O has a maximal element here. And then we're trying to draw contradiction again. Okay. So O has a maximal elements means what? Yeah. So means what? A is in O, right? So A is in O means what? What is O again? It's a collection of open cover such that it doesn't have a finite subcover. Okay, good. So if you consider A intersect with your subbases, okay, if this cover X as a cover of X by subbasis element, what do you get? What's the condition on every cover of subbasis element? Huh? What's the condition? Every cover by subbasis element has a, what's the assumption? Forgot. Two assumption only, forgot already. Has a finite subcover. So this thing has a finite subcover. But A intersect X should be just A, right? It's just A because subbasis is the thing that can generate your topology, right? It's just A. So this contrary that A having no finite subcover. We just break the A down into subbases. This thing should be just A. Because A is an open cover, right? And then I intersect with subbases means what? I look at A as the union of subbases element. So 没有，有两种情况你要跟人家 argue 的话，一种情况你要告诉人家你想什么，第二种情况你要听清楚人家在讲什么。你两个都做不到，你要讲跟人家讲话，对吗？除非你给我一个 argument 说为什么不是啊，不然你就听不懂人家讲话，这样我们要讲什么话呢？我们讲不到话，你懂吗？你明白吗？所以你要告诉我为什么不是，然后我就 counter 你哦，为什么不是？不然我已经跟你讲不是，然后你又不懂我在讲，对不对？讲不到话这样子，所以这是无效沟通。所以你要学数学啊，就是要教你讲有效沟通。OK，所以你们老师都没有跟你沟通，所以他没有教你沟通的。这些老师不是在教数学，我不知道他们在教什么。OK 了，所以你学了数学，你就要跟人家 argue。对吧？你学逻辑啊，第一年就教你做 discrete map 啊。如果你只会 true for true for true for，没有用，可以丢了，那 truth table 要 apply。
正常的 set operation 来说，
正常的 set operation。OK，我私下说给你，我现在不要说，因为我们不要浪费时间。可以，我私下我欠你一个东西，你记住一下。我欠你一个，OK，OK 啊，好，OK。So now in this case, then we'll say that A intercept X does not cover X. Okay. Alright, now we will suppose that it doesn't cover X. So what can we do? It doesn't cover X, right? So this means I can pick something out of the complement. Okay, I take something out of the complement because it doesn't cover it. Cover 到吗？有人在它的 union 以外。Okay. So what can I do next? In this intersection, it doesn't cover, so there should exist a U in A, okay, such that X is in U. Okay. Okay. OK，我知道了，这个不一定不应该等于，不一定等于。But 如果你比它小的东西都 contain finite subcover 啊，then 这个 finite subcover can work for the bigger A. Yes, this is the argument. That's right. It doesn't equal, it might not necessarily equal. But if you have a smaller subset that contain a finite subcover, then this finite subcover should work for the larger A. Okay. Yeah, this one is better. Yes, right. Okay, thank you. Okay, so now, why can we find this U? Because A is an open cover, right? Okay, so we can find this U. So what can we do next? We haven't used subbases here. So what I can do next is, since X is a subbasis, what can I do? There exists finitely many subbasis elements such that X is inside the intersection of this subbasis. Okay, because this is the topology generated by subbases. Okay, you live in some finite intersection. Does it make sense? Okay. Okay. So what? So not that this S was not covered by A, was not covered by A intercept, was not covered by let me think, how should I put this? So this guy here, this X here, is not covered by A intercept X, right? Okay. And then what should I argue here? Let me think. So what should I argue here? Since X was not covered by A-intercept X, what can we get? Let's think. What can we get here? Okay, so what we can do is, I think, how should we put this? So what I want to claim here is, yeah. Let me think, what you're saying. So, this is a U. So, what are you trying to say? If I have a U in A, that is a subbasis. If you have X in U intercept. No, this is the intersection line inside U, not X1 line inside U. It's the intersection line inside U. X is in U.
One.
Mm-hmm.
So that's it.
It's covered in A intercept X. Say again.
X in
Mm-hmm.
U
X is in U. In A, yep.
and X.
But slowly a bit. So if I have a U, let me think. So what is this A? A is an open cover, right? So it's a set of open set. Okay. So I have a set of open set, and then I intersect with the sky, some basis. Okay. And then X is in U. X is not in X is in this complement. Okay, so what's this complement here? So you can think of a open cover, right? You make it smaller somehow, right? You make it intersect with the sub basis. Okay. And then what do you do? Because A is an open cover. Okay, so I mean, let's draw it. Maybe I got this X. Okay. I have a point here. And then I have maybe A. A have to cover it. But what happened to your sub basis? And maybe your sub basis avoid this point. Okay. Possible. So that's why we want to have a contradiction here. Sorry. Oh, yeah, cover X. Okay, so sure, also cover, but somehow their intersection. So there's a contradiction. I mean, yes, it's true. We want to draw a contradiction here. So suppose it exists. So suppose somehow this two intersection need to like still cover, but still cover, but somehow they avoid each other such that there's a non-empty intersection. Yeah, maybe you can draw different contradiction, I guess. I think you want to draw a different contradiction. Yeah, but maybe this contradiction is a bit different. Yeah, you can try and draw your contradiction. You can continue your way of thinking and then try and construct your contradiction. Maybe you want to contradict that subbasis is not the topology is not generated by subbasis, is it? But the contradiction here is different. Okay, so let's see what's the contradiction here. Okay, you can try and use your line of thinking and then see you got other contradiction. Okay, so let's say this happened. So let's say this happened, and then surely the next thing will happen because we are following definition only. Okay, we are just following definition. And then what I want to claim here is, if you take A union with Sj, it should be an open cover of X. Okay, this is what I want to claim. Okay. From this result here, I want to claim this. So if you take A union with this, one of them is enough, okay, to cover your X. Okay, one of them is enough. This is what I want to claim here. Okay, this is what I want to claim. If this happened, what happened? A is the maximal element that has no finite subcover, but this one is larger than A. So meaning this guy has a finite subcover. Okay, so since A is the maximal element, okay, that has no finite subcover, there's no finite subcover, then A union Sj must has a finite subcover. Correct or not? Because A union Sj is larger than A. Okay, A is the largest one, doesn't have a finite subcover. Okay, so what's the next trick we can play here? So what we can do here is you can consider X living inside the intersection of all these guys. Okay, and then we're going to play a set theory trick here. So what you can do is this thing is living inside the union of let's see, union of I1 to N of AI union with intersection of this. You can try and prove this. Okay, you can try and prove this. So many I's, will you confuse or not? I think you might confuse. So let me put J here. Like this. Okay. You can try and prove this set inequality here. And then what's this thing is this thing is in the union of AI, union U. Okay. Because the right hand side here is living in U. Okay. So what have we done here? We only got NAI and 1U. So this means that this is a finite subcover of X from A contradicting is in O. Okay. Okay, so there's something, maybe this part need to check here why this claim is true. Okay, but this is the proof for this subbase theorem, Alexander subbase theorem. Okay. Does it make sense? Okay. 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 And then next, we were going to use this to prove the Tychonoff theorem. Okay. We'll prove it and then we'll take a break from there. Is it okay? Yeah. So let's see how we use this Alexander subspace theorem here. So let's prove the Tychonoff theorem. So what is the Tychonoff theorem here? Actually, we have two direction of statement. So it says that a product of compact space is compact, and also say that if the product is compact, also implies that every factor xi is also compact. So there are two directions actually in this Tychonoff theorem. Okay. Actually, one direction is easy. Which direction is easy? This is the exercise you should do whenever you see if and only if. Always one of the direction is easy than the other. You should train yourself to see which one is easier. Huh? Where's the converse? Surprisingly, that one is the hardest one. Yeah, surprisingly, that one is the hardest one. How to piece all the compact thing together to make compact space is harder. But if you had the whole thing is compact, this will imply all the factor is compact. Why? Yes. Consider projection. Projection is what? Projection is continuous. Continuous. So every SI can be understood as what? Continuous image of a compact set is compact. Every xi is a continuous image of compact product set xi. Okay, so this direction is easier because projection is continuous. Okay, but to prove projection and continuous is another story. Okay. Sorry? What do you want to prove? You want to prove xi. What is the function that gives you xi from product of xi? Yes, so let's say I want to talk about x. Let's say my I is going from 1 to n, right? So if I want to talk about Sn, how these two related? Key off. So what is key off? Mathematically. How to remove? How to remove? How to remove? How to remove? So I got x1, x2 up to xn, right? I just want Sn. So what do I do? Use what? Matrix? Yeah, you can understand the projection as matrix, but this one is for finite case. Or finite case, you can deal with matrix. Or that's why linear algebra is just finite dimensional. You do infinite dimensional, how do you write down the infinite matrix? Okay, so there's another word for it. Projection. I project to that element. Okay, so I project. So this is the projection. So meaning you don't understand the projection map. So now do you understand what the projection map is? Huh? No. Yes, but not precise enough. I want to project to one of the coordinate space. Not just infinite, I can do projection on finite case also can. Okay, no. Then in this case, I don't need to discuss about matrix, no? Oh, another case is if you want to discuss about matrix transformation, what do you need to know about matrix transformation? It has to be linear. The map has to be linear. If it's not linear, then you cannot write it as matrix. That's why the first year algebra called linear algebra. Because what you learn is linear only. Okay or not? Okay, so that's why now we go to abstract part. Why is it abstract? Because we no longer have linear algebra. We only have projection. I don't need to write matrix for you. I just tell you which coordinate I keep. That's all. Okay. Okay. Okay, good. Okay, so the other direction is the headed part. So how to do it? So suppose xi, ti is compact. Let's suppose it is compact. So why we want to reduce to sub-basis? Why we want to reduce the case to sub-basis in the Alexander case? Now we want to show a product space is compact. What's the topology on product topology? How do you form the product topology? Check. Go back and check. How do you form topology for product topology? Check. The other is box, right? Box is easier, right? How about the other one? What's the product topology? As a basis? As a sub-basis. Yeah, as a sub-basis. So the product topology is generated by sub-basis. Okay, so that's why we want to reduce the question of showing every open cover is finite to just open cover by sub-basis. Okay, does it make sense? Make sense or not? Okay, so we reduce to show for every open cover to just open cover by sub-basis. Okay, because we know that our product topology is built up by sub-basis. Okay, does it make sense? Okay, okay. So, what are these sub-bases? So let's consider X to be the product space of this guy here, Xi. Now, let the sub-basis to be the inverse image of every open set in Ti. Okay, and then this form a sub-basis. Okay, this is how we build the product topology. Okay, so by the Alexander basis theorem, what do we need to do? We need to show that every open cover by sub-basis has a finite subcover. So in this case here, need to show for every, right? So we need to take any open cover by sub-basis. Okay. Right. Right. So what do we do next? What can we do next? So we want to find a finite subcover that cover X from here. This set is quite big. Okay, it's quite big. It's quite big. So can we somehow reduce it or not? Okay. So let's consider for each I. Okay. Let AI be let me see. Yeah, I think this is okay. So let AI to be the open set such that Ti such that pi inverse U is in A. Okay, so we consider each layer. Okay, each layer here. So the claim is, so here's the claim. There exists I naught in I such that this AI naught should cover one of the coordinate. Okay, one of the layers should be the cover of one coordinate space and one factor. The claim. Okay, we're gonna prove this claim. Okay, we're gonna prove this claim. Otherwise, okay, by contradiction. Otherwise, for every I in I, there exists some point that you cannot cover using your AI. Correct or not? Okay. Then that means what? Then you are in trouble. Why? Why are you in trouble? for every xi, you can find some point that cannot be covered by this AI layer. So if you get a collection of this point inside your X, it is not covered by your A. Okay. It's actually not covered by your A. Okay, so this contradicts that your A is a open cover. Okay or not? Does it make sense? Does it make sense? Okay, so now what we do is we manage to reduce to the open cover that cover X, found a smaller layer that cover Xi, no? But this is good, oh. Why is this good? We know that every Si is compact. So this means what? I can find a subcover of AI node that cover Xi node. And then the magic thing is the inverse image of this guy will cover the whole thing. Okay, so this is the subcover U1 ... UN in I node. Then the magic thing is if you just consider the pre-image of this UI, this guy is already enough to cover your X. Okay, it's enough to cover your X. Does it make sense? Where the last term here is the magic part. So you use the finite cover that cover one factor ring, not ring, factor space. Then you look at the pre-image, it is the finite subcover that covers your X. Okay. Yeah. Does it make sense? What's the inverse image of one of the open cover? Should be U1 and then XXXXX everywhere. Okay. Yeah. Does it make sense? Can see Y cover or not? Every other coordinate is just other thing, xi. But I managed to cover xi node already using finitely many things. Okay. Does it make sense? You should think of the pi inverse using this map here. This map. So what's the inverse image of Sn? Sn plus everything here, everything. Okay. So here we reduce to cover X to cover a compact Xi. Okay. And then to cover compact Xi, I just need finitely many things. And then if I look at the pre-image of the projection map, then this set is enough to cover the whole space. Okay. Make sense? Okay, any question? Hey, did I solve your question just now? Is it enough to solve your question just now? The A intercept X is not equal to A. Okay, enough. Okay. Yeah, thank you. Yeah. Yeah. Any question? In case maybe you go back and revise. Hey, somewhere got problem. Okay, bring it to the next class, and then we can settle again. Yeah, just that now I don't want to disrupt the flow. Okay, because we have quite a lot of things to say. Any question before I take a break? Can ask. If I cannot answer, then I can answer next time. Anything you think ragu? So what is ragu? Huh? You have doubt. Okay, you have doubt, you can ask. Feel free to ask. Yeah. If you think of it after class, also can ask after class. Okay, if not, you can get some snack here. If not enough, maybe you guys have to share. I only have one. This one is my childhood favorite. I don't know if you eat this before, no? See this before? No. Hey, you should try. Hey, we should let the Chinese Chinese classmate try this. See if you think how is it. When I was a child, I like this a lot. You guys should try. There's a tomato sauce inside here. Promoter. Okay, and then this one is also quite good. Green pea. Thing. Yeah, try this. Okay. Okay, let's take a break until 1:08.试下你们，大家猜看这个，没有吃过，很神奇这个。对对。以前我家外面的那个杂货店有卖，然后杂货店关了，我就不知道去哪里找。哎，有大包啊，我有大包啊，对，有大包啊，但是我都没买那个小，看到没？
这个我以前吃了一样。
是哎，
还买一个是辣椒酱。
哦，有，但是我们对通了，因为我买那种一大包啊，它包混了，漏包漏那个钱。可以，吃吧，拿去吃，拿去吃。呀，哦，OK，可以。就这样分给你的同学看一看。可以。等他，你看了吗？还要看。好，来，你来看。味爆诶。我觉得那个 tomato sauce 是我小时候味道，但是我有点忘记它的薯条味道了，吃起来不太像以前吃的。try 一下，下次再带多一点。
跟你讲，还有一个在里面，这个也没有在里面，
应该是在锅里面啊，是吧？不一定要在那个什么里面，在 order set 里面 ，totally order set。
不懂啊。
upper bound definition。在那个 display 的东西，有一点点差别，不是？我忘记什么差别了。About of，没有差很多应该。Yeah，它可以，我想想，它可以活在皮里面，它不一定要活在那个 totally order set，活在 original 的那个 set，说它活在 all 里面。对。才 proof claim 了才 proof。Gary？ 哦，还没有来，怎么？
准备了。应该是刚才上面。
OK，什么3门？
就设计了一个版本。
你跟他一样课？
哦，然后我也是要回去看。
哦，你要赶上？对。我觉得你刚才可以 try 你的那个直接 contradict 什么，它不是上笔是否
好没有，因为对，我是可能这个世界。我一开始我想到你就是这个东西来的。你这个
一个是
A intersect S 火焰，
然后
然后你讲是这个。
random intersection， random intersection union of random intersection， 这个意思是
random intersection 应该这个。
random of， 看一下，这个一样是因为我 start with， 这个是 我看看啊，
那个
那我
蛮好玩的，
讲读啊
蛮好玩的一下。
，OK 啊，这个应该是刮胡在这边，挂在这边嘛，对不对？
啊，
这挂的这样的，对，
哦，
对吗？
但是哦对，但是你 AJ 你没有讲怎样
嗯
选出来它就出来了。
AJ 啊
哦，
，AJ，你说是 SJ 耶？SJ 怎么选出来？
但是就是这个，
因为
我懂
SJ 跟 AJ 是诶，
它
我想一下
不一定要，一样数量嘛。
我想一下啊，诶 AJ 从哪里出来啊？确实诶，AJ 从哪里出来？我想一下
啊，
，AJ 应该要从这句后面呢，是不是？想一下啊，我想一下啊，
啊，
哦，应该会不会这个放错了啊？诶，这个不会放错吧？你是说为什么还 finite？
嗯，差不多。没有啊，但是你讲没有放在上好，它也不会放。
哦，我知道了，啊，哦，我知道了，我知道了，哦，对，这个是从这里来的，应该从这里，从这里，从这个才会给出这句话，所以这句话为什么涨价呢？一个想一下，
这边
应该要其他的东西，
啊，因为这个东西放在应该是这样，
哪一个？这整个东西翻的
这个东西放的。
啊，没有这个东西翻的，这个翻的，每一个 J 这整个东西有一个 finite subcover，然后我应该要拿它们的 intersection，有写错东西。
因为下面这是要 proof 这句来的，所以我们
不，这个 proof 到了，这 proof 到了，这个 claim 过后，因为这个比 A 大了嘛，A 是最大没有嘛，但是你比它更大，所以你有了，
哦，
有了过后我才有这个 AJ，我是不是写错这个东西啊？我想一下
这样子没有
吧
，AI 啊，
，AI 吧，
然后
从 I
接
到零，I 等于1到 L，就是 Unit S，
啊，因为 S 就是 fix 的，
对，S 是 fixed 的，
XJ 是 fix 啊，
对，S 就是
我想一下啊，
就只是表示还有，
这样应该 make sense 啊。
对，那这样就可以用表对，
OK，这样的话，OK，哦，这样比较 make sense，
啊，就对，
哦，这样就 make sense，这样 make sense。
哎，
哎，喂，make sense 没？
对吧？
等这一步去这一步诶，
因为这个 subset 这个啊，
这个 subset 这个面哪里可能？
对，
这样
这个更小啊，是有写错吗？这个应该是要 finite intersection of 这个 finite cover 跟另外一个 finite cover，懂吗？我要写这个东西，
不懂，
就是一个 SJ，我有 finitely many 吗？
嗯，
我有 finitely many SJ 吗？我要 intersect 全部 finite subcover，懂吗？我要 sum I，我要 sum J，
啊，
我要 intersect I，我要 intersect J。哎，给我想一下，
嘿嘿，
这个 part，我想一下，说这个有 finite subcover 吗？说 sometimes I think 我们可以写成 AI union SJ，然后 I 到 N 是不是？对不对？然后现在我应该要拿所有的跟它合在一起，
嗯，
所以我要拿 union of 这个 intersection，对不对？我应该要做这件事情，泄露东西啊。我应该要 intersect，所以说怎样写啊？想一下
假如有点的兴趣，全部
，intersect J 啊，我想一下，怎样 fix 这个东西啊？OK， Okay. I will try and write out detail what is going on just now inside those proof in the lecture note. And then maybe you can discuss again next time. Okay. The next thing we want to discuss is the stone check compactification. Okay, so I think you will often see this in a functional analysis. So when do you have a stone check compactification? So last time there's one compactification we saw before. Do you still remember? We have saw one compactification before. Yeah, so what did you add? You just simply add a point. Okay, you add a point and then you compactify it. This is somehow we regard as a minimal compactification. Okay, you just add 1 point. But this stone check compactification that we're gonna introduce is somehow the maximum. Okay, and then we will show that this compactification is unique up to homeomorphism. Okay, so in our space is up to homomorphism, homeomorphism. If you study groups, then maybe unique up to isomorphism. Okay, so depends on what object you study. So somehow this compactification is a maximum one. Okay, that we're gonna see. Yeah. So let's define again what is a compactification means. So what does a compactification of a space mean? First of all, this space has to be, so if I want to say that Y, okay, is a compactification of X, first of all, this space have to be, okay, this is a subset, sure. Okay, so this space contain X as a subspace, and then what is the description of this X here, Y here? Compare, obviously, otherwise, what is the compactification means? Okay, so this Y have to be compact, and then we want something stronger. It have to be Hausdorff. Okay, I want to be able to separate 2 points. Okay. So this is a compact Hausdorff space containing X such that if you take the closure of X, it's already Y. Okay, so meaning if you put in all the limit point, it is Y. Okay, and then we will say that two compactification are equivalent. If there exists a homeomorphism between, let's say, y1, y2 here, y1 and y2 are homeomorphic, okay, such that hx equals to x. Okay, so on the space itself, okay, it is identity. On the subspace itself is identity. Okay, at the whole space, it is a homeomorphism. Okay, so I can like do random stuff on the limit point of x, for example. Okay, but have to be homeomorphic. So you need to be able to transfer the topology information across. Does it make sense? But require identity. Identity on that. So what's this h here? Also, this h here is this homeomorphism. Okay. So if you restrict h to x, it is identity. Okay, on the subspace of its identity. Away from subspace, you can do some random stuff, but need to be homeomorphic. Okay, so from this remark here, from this definition here, actually what can you see? Actually, you can see quite a few things already. So remark, not that a compact Hausdorff F, last time I think I asked you to do in the tutorial, this space is actually normal. Okay, normal. Okay, compact Hausdorff implies normal. So you can separate 2 points and then you are compact. That means you can separate 2 disjoint closed set. Yeah. So you are normal space, right? So by what? By the Arison lemma, what do we get? If you are normal space, then there exists a continuous map such that you can differentiate 2, you can separate 2 closed set, disjoint closed set. Okay, so this implies that Y is actually T 3.5. Okay, completely regular. Okay, T 3.5 into 1. So completely regular is hereditary. Okay, so this implies that X is also completely regular. Okay, so that means there exists a continuous function such that you can separate. What's completely regular? Separate point and close set. Okay, a function that can separate the two. Okay, so you can ask another question. Can I go backward or not? Okay, can I go backward? So now we say that if it has a compactification, then the space you started with have to be completely regular. Can you go backward? Backward is what? If X is completely regular, can you found a compact Hausdorff space or not? Such that it is its compactification. Okay, can you do that or not? Yes. In fact, the converse is true. Okay, so in fact, the converse is true. So if the converse is true, if X is completely regular, then X has a compactification through an embedding in a compact Hausdorff space. So you might worry, if my S is completely regular, can I always embed into a compact Hausdorff space or not? Can or not? Does this embedding always exist or not? What's this content here? You want to embed X into a compact Hausdorff space. Last time, what did we prove? A recent metrization theorem, what did we prove? We proved that every what kind of space is metrizable? Every completely regular space. What's the metrizable theorem here? What did we prove for a recent metrization lemma? Every second countable regular space is metrizable. Okay, every second countable regular space is metrizable. Okay. But what did we use? We use the fact that second countable regular space is normal. Okay, and then we try to embed what? Embed this space into a metrizable space, infinite product space of R. Okay, and then I make a remark there that we not only can embed into this infinite space, I can actually embed into this product of actually compact space. Okay, infinite product of compact space. But just now we proved that it is compact. okay, by Tychonoff theorem. Okay, so we didn't go through this proof, but this is just a remark. So we're gonna use this remark here. Okay, we can embed this kind of space into a compact Hausdorff space. Okay, and then the claim is this embedding here will give the compactification. Okay, so this is actually a lemma. So what's the lemma here? So this one have to be proved actually. Be proven. So lemma, consider X is a topological space, and then suppose H is an embedding of X in a compact Hausdorff Z. The claim is then there exists a compactification Y. Compactification Y of X such that it has the property that there exists an embedding from Y to Z. Okay. So first of all, you only have little h that you can embed X into Z. But now, okay, you will have a compactification of X such that there's an embedding from capital Y to Z. That when you restrict to X, it is just little h here. Okay. And then what you do here is you need up to equivalence. Okay, so what you do here is you need up to equivalence. And then we will call that this compactification is induced by the embedding H. We will see a bunch of example later. We will see a bunch of example later. So in this case, what do you think? How are we going to build this Y here? What's the recipe of building this Y given this little h here? What's the recipe? So let me draw something for you. So I have an X here, right? Okay, I have a Z here, for example. And then I have a map H, little h. Okay, I can make this X into some little hx. So this is the embedding. So how am I going to build my compactification here? How am I going to build compactification here? Suggest by the definition. What does the definition says about compactification? Is a what? Hausdorff. What else? There are a few things to satisfy, right? Hausdorff, compact, and then how many things? Hausdorff, compact, contain X as a subspace, such that X5 equal to Y. So you should take closure of hx. So you should take this hx bar. Okay, you should define this as your Y. Does it make sense? So there's a how to say technical part here. So actually, this hx here, we should call it x naught. Not exactly x, but it's x in some other space already. 怎么理解这个东西啊？就是 我不知道你有没有一个心爱的东西，有没有一个心爱的东西？你想一想，可能我心爱的东西是这个水壶，我很爱它嘛，对不对？我觉得它不是水壶，诶，它是一个可以帮我装水，又我很喜欢羽毛球，所以它好像有羽毛球在里面。但是对你来说呢，它只是一个 embedding 在这个 R3 里面，它只是一个普普通通的水壶啊，就是一个铁做的 plastic 盖罢了。这个是 S n o 但是对我来说呢，它不只是水壶，它就是它自己，对不对？就是我也不知道，就是对我来说，它就是不是一个普通水壶吧。这个在我心里，这个在客观世界。Yeah. Okay. So what do we do here? In principle, we should set this hash x to some s naught. And then if you take this bar here, this is not exactly y, it's just y naught. Okay, it's just y naught. So how do you form y actually? Actually, it's not too hard to form the actual y. Okay, it's not too hard to form the actual y. So what do you do? What do you do here? So this is the technical part. So this is the technical part. So how do you do y? So actually we define y to be x union a, some set of thingy. Okay, what's thingy here? So with x intercept a should be empty. Okay, they should be empty, such that we have a bijection. Okay, bijection between who? Between this 也是活在心里的一个 y 和一个客观世界的 y， 我 embed 它进去。What kind of bijection here? So I simply send x to hash x, 客观世界的 hash x. If x is in x, and then in A, how? What happened in A? There exists another bijection with k is also a bijection from A to y naught minus x naught here. 你觉得很悬啊？其实不会悬。我告诉你一个东西，比如说 I give you an example. Okay, I give you an example. So I give you an example. So let's quickly go to this example here. So let's say I embed this open interval here. Okay, into x1. How do I embed this? Okay, just two questions. How to embed this? T2. Calculus 2. Cos 2 pi t sine 2 pi t. Okay, so what do we do? What do I do here? What happened to this interval here? It get mapped into R2. 客观世界. How does it sit inside here? A circle. Missing a point. Which point is missing? 1, 0. This point missing. What's the closure of this picture? Put in this point. But how to realize a circle here? I mean, how to realize the dot here? Yes, just a sum bijection, random. So usually people will call this infinity point. If you want to call it 缩宁 point also can. Okay, ma, bijection only. Random lah. Okay or not? Okay, so these two together build out this complex space. Okay, the union of these two is the y. Okay, this side is y naught. Does it make sense? Okay, but you think, hey, 这边没有 combine, 这边有 combine 呢？是不是？怎么想这个东西？ Okay, So how do we think of this thing? How to think of this y? Actually, we need to make this h into homeomorphism. Actually, we need to make this into homeomorphism. How to make this into homeomorphism? This is very much how we topologize this z at y here. What are the open set here? Okay, so we will topologize the y such that the h is a homeomorphism. So meaning what? I will call everything open in U is open in Y if and only if HU is open. Okay, if only if HU is open in Y not. Okay, 把它编程式就对了。So meaning whatever topology I have this on this Y not here, I should have it on here. So that's why you'll see people drawing circle like that. And then without mentioning I'm in R2, R3, or what kind of any ambient space. No, people just talk about this. Because I move the topology of circle to a random space. 我心里的世界，好不好 ？OK 吗？明白吗？我把客观的东西搬进我心里了，好不好？可以吗 ？Make sense? Okay, we'll see more example. Actually, this proof quite technical. Other than showing this is homeomorphism, and then already homeomorphic, right? So you need to show the subspace thingy, and then you need to prove uniqueness. Last thing, okay, you need to prove uniqueness. So it's quite standard. I'll leave it. So let me give you some more example. So this one last thing is you need to show. Lastly, okay. So I will say that check all compactification property. And then lastly, you show uniqueness. Then you are done. Okay. Showing uniqueness is quite standard. Okay, you can try it out, but I will put inside my notes. Okay. So we have looked at one example, right? This one point compactification. There's another way to compactify this 0, 1. Do you know? You know how to compactify it? Somehow I give you the hint. Let's say we do this embedding here. Okay, if embed normally on real line. What is this compactification here? Hey, Jimba, how to compactify this open interval? What are the limit point of 0, 1 inside real number? 0 and 1, right? So I just close it. Okay, so H01 bar is just close interval 0, 1. So this is called a 2-point compactification. Okay, I add in 2 points. Make it into a closed interval. 2-point compactification. Actually, there's another way to compactify this line, you know. I'm not sure you remember or not. Where did we map this 0, 1 again? There's one very special space. Let's consider up to -1, 1. Anyone remember the topology sine curve? Anyone remember this line here? So it starts somewhere at 1. 1, where is 1? Should be 1 sine 1, right? Let's put it here. And then what this graph do? Oscillate infinitely frequent around the origin. Last time we say what? Where's the limit point? All the way from 0, -1 to 0, 1. So you add in this line here. So this whole thing form a compactification of the interval 0 to 1. Okay or not? So we embed it in different way, then we will have a different compactification. Okay, but what do you observe here? What do you observe here? I write my 1 point using two continuous function. Using two continuous function. One is x, one is sine 1 over x. So what did I do? I add in the limit point for x. I also add in the limit point for sine 1 over x. So all together, I add out this line here. Okay, so I'm trying to fill out the limit point for each coordinate. Then I fill out this line. Okay, so this is the starting point of Seng compactification. Later we will mention we use continuous function. Okay. Okay, let's do one more exercise and then we will mention about Seng compactification. So there's another way to embed. This is a calculus 2 example also. So from 0, 1, I can homeomorphic it to 1 to infinity. Okay, and then what do? I try to map it to R2. Okay, so how do I map it? So I use the polar coordinate here. Okay, theta to 1 minus 1 over theta. How to plot this graph? This is the polar graph. How to plot this graph? When theta equals to 1, what happened? 0. Okay. You can see that when theta increase, right? What happened to this radius? Increase also. Okay, but the maximum is, the supremum is 1. You never reach radius 1. But the theta is periodic, right? Let's say this one is radian. If it is radian, what is the period? Okay. 2 pi. 2 pi in real number is what? 2 pi in real number is what? 6 point something. Okay, 6 point something. So meaning what? When you increase your radius up to 6 point something, you need to turn a full circle already. And then you keep increasing. So this one should be a spiral. But this spiral will get infinitely close to where? The unit circle. So where's the limit point? Limit circle. Okay, so if you take the closure of this embedding is you have this spiral graph and then with the unit circle. Does it make sense? Does it make sense or not? Okay. Okay. Can follow? Limit point, you take a point and then look at there's an infinitely many points in the set. Okay, good. What time is it? 1:36. Okay. So just now what? Let me see which part we want to go here. I think maybe we can show a jump. Let's say so just now we say that you see we are we are adding the limit point for continuous function here in this 4 case here and also in this case 3 here. Okay, so what if you consider all possible continuous function that you can define on X and then you take the closure? Crazy or not? You take all possible continuous function that you can define on your space X and then take the closure of this embedding. Crazy or not? Okay. So let me write down the statement here. So this is a theorem, a very nice theorem, very good, nice theorem. So a space, topological space, has a compactification. Why? Having the property that every, okay, not just continuous, actually we need to talk about bounded. Otherwise, it's very hard. every bounded continuous map, okay, f from x to r that can extend, okay, extend uniquely, okay, uniquely to a continuous function, continuous map of y into r if and only if it is completely regular. Okay, if your space is completely regular, then you can do this kind of compactivation. Okay, and then we will call that the compactivation that having this every bounded continuous map that can extend uniquely to a continuous map here is called a strong check compactivation of. Okay, so this is a theorem. So I mean, I haven't quite show you that I have formed this after I formed this I haven't quite show you that after I formed this compact set here, okay, how do I extend the map? Okay, how do I extend the map? How do I extend the map? In a unique way. Okay, how do I extend the map here? So how does it extend to a continuous map? So what do I mean here? So let. So how do I extend H? Okay, how to extend H to so in this case here, what do we want to extend here? Let me think. So what are we extending here? We should extend so let's see, how do we extend the graph fx equals to sine x. So this one is from this graph is going from where to this continuous map is going from 0, 1 to r. Okay, how do we extend this continuous map to a map from let's say G to a continuous G from the closure of 0, 1 to R. Okay, how do we do this? Okay, so the question turned to this question here. Can we extend this function? Okay, how to do this? So we're going to use this graph here to help us do this extension. Okay. So you need to extend such that when you restrict to 0, 1, it gives back your F map. Okay, how are we going to do this? How are we going to do this? Don't know. How this set sitting in you know how is this set sitting in R cross R? So how this set sit in R cross R? What's the coordinate here? What's the embedding here? 0, 0, 1, 0. I mean, in a, I mean, in a consistent way, how do we do it? X should send to where? Okay, how we sit inside here? How does open interval here sit inside R plus R? X, comma, why is it 0? Is this 0? Why is that? Why is it 0? Two coordinate here, right? Sine and sine 1 over x. So this is how we place our open interval inside R2, right? The topology's sine curve. Okay, if x0, we cannot trace out the topology sine curve. It's just a normal embedding. Then that in that case, it's just a 2-point compactivation. So we have sine over 1 over x here. And also there's another infinity point, right? This point, we send it to 1, 0. Okay. And then how do we split out this f? The way we split out this f is we can just consider a projection on second coordinate. Then this will help us to project to sine 1 over x for the point in 0 and 1. Okay. So where's the extension here? What's the extension here? What's the G here? What's the extension then? Extension is a map from the compactivation to R, right? Okay. Such that when you restrict to the subspace 0, 1, it equals to the continuous map that we want to extend. So if you look at this chain here, what does this change do? You simply just compose pi2 with this. Let's call this an embedding edge. Does it make sense? Yeah. Okay. Yeah. Okay. Of course, you need to show why is it unique. Okay. Yeah, but this is one of the extension. So this extension is a map from the compactivation to R that extend the map from the subspace 0, 1 to R. The map from 0, 1 to R. Does it make sense? Okay or not? Okay. So so the theorem here is if you have a property that every bounded continuous map can extend area, then this is called a Stonechek compactivation. When can you do it? Whenever your space is completely regular. Does it make sense? Okay or not? Any question? I think we have to stop here. Maybe we put next time. Any question about Stonechek compactification? Okay. Do you understand what this theorem trying to say? Understand what this theorem trying to say? Can I mean, you need to have, if it's better if you have one example in your mind, which is the topology sine curve. Okay, so you want to think of extending the map sine 1 over x. Sine over x, 1 over x map 0, 1 to R. Okay, and then you want to extend this map to the closure of 0, 1. So the closure of 0, 1, which closure you take? A lot of closure, right, depend on what embedding. 1-point compactification, 2-point compactification. But in this case, we take the closure of the topology sine curve. Does that make sense? Okay, no. If it is the stone check compactification, then this extension is unique. If not, maybe not. Okay. But in stone check compactification, you need to check for all bounded continuous map, not just one. Where it's all, every. Okay. Maybe if you like in this case let's do some homework then. So homework. What is the stone check compactification of the open interval 0, 1? Okay, let's do this homework. What is this? Okay, after you can extend all the bounded continuous map, what the space have to look like? The compactification of the space. Okay. Yeah. Now let's do this homework. What happened to the space after compactification? Okay. Okay, any question before we break? No? No? Okay. Okay, right. So maybe I will try and fill in some detail. I think there's some doubt in this what proof is it? Alexander subspace theorem. Okay, let's add in more detail. Let's see. We can discuss again next in the start of next lecture. Okay. Yeah. Okay. So see you tomorrow.